Good day, Morgans. Our topic ngayon would be ESAT 4, transmission lines. This is Engineer Randy Aliado from Morph, Cebu. Okay, these are our subtopics ngayon. We have types of transmission lines. We'll be discussing the coaxial connectors, then the characteristic impedance, the velocity and phase shift in your transmission lines. Then let's compare the resonant and non-resonant lines. Then the transmission lines as circuits, then impedance matching, and lastly we'll be talking about the principles of Smith chart. Okay, so let's define what is a transmission line. So this is a device designed to guide electrical energy from one point to another, and it is a conductive connection between system elements that carry signal. Now, when you deal with transmission lines, we could trace back from the introduction to electronics communications natin that in a communication system, there must be a transmitter, and there must be a receiver, and there must be a medium. So we can actually choose a medium that is, let's say, free space using antenna, or we could directly connect it with a line. So this is now your transmission line. So the problem with respect to this free space medium is that it's open to all the noise available in the free space. So kaya nga sa ating illustration last time, we know that the noise is pumapasok sa medium and wala tayong protection dito sa free space. So in order for the noise to at least ma-minimize sa pagpasok ng ating medium, we could create a medium that is well designed para ma-immune yung sarili niya sa noise. So with that, hindi masyado makapasok yung noise sa ating entire system because protektado yung ating transmission medium. So isa sa kino-consider natin as a good transmission medium is yung transmission lines. So now, if you will look at fiber optics, whether it is a transmission line or not, we can say that it's not a transmission line because it's not a conductive connection. So pag sinabi mong transmission line, it's made of conductors talaga. Fiber optics can be referred as the transmission medium, but it's not under the transmission line. So it's still a guided transmission medium, but not a transmission line because nga wala siyang conductor. So transmission line must made up of at least 2 conductors. Yun yung kailangan natin para makagawa ng transmission line. So primary requirements for a transmission line or of a transmission line is una-una, dapat minimal yung attenuation. Ibig sabihin, hindi lahat or hindi malaki yung loss within the source to destination natin. Then pangalawa, it does not radiate any of the signal as radio energy. So ibig sabihin, if it is a transmission line, the signal must be contained in the transmission line while it is traveling from source to destination with minimal na loss. So kung iisipin natin, if ito yung requirements ng transmission line o para matawag na transmission line, then it means also na yung goal ni transmission line is to achieve maximum power transfer, diba? To have a minimal attenuation and to not radiate your signal but deliver it to the load means you need to achieve maximum power transfer in a transmission line. So in order to achieve maximum power transfer in a transmission line, we need to observe this following. So unang-una, you need to connect a balanced line into a balanced load or connect an unbalanced line to an unbalanced load. So that is one. So pangalawa, you need to be considering that the load must be a purely resistive load. So that is pangalawa. Pangatlo, it needs to be ZL is equal to ZO. So that would be the third. So these are the 3 requirements para makabuo tayo ng maximum power transfer. So yun yung pag-uusapan natin along the way. Okay, so now let's begin with the types of transmission lines. We will discuss 3 types. Yung pinaka-major types of transmission lines, the parallel wire, coaxial lines, at saka twisted pairs. So parallel lines, from the word parallel, it means dalawang wire ito na magkatabi sa bawat isa. So these are made of 2 parallel conductors separated by at least mga 1/2 inch to 7 inches depende sa uri ng wire mo. So aside from that, meron siyang mga popular na uri. So kagaya ng open wire at saka yung twin lead. So the open wire is rated at 600 ohms, whereas the twin lead is rated at 300 ohms. So we have 600 ohm open wire and we have the 300 ohm twin lead. So the difference between the open wire and the twin lead is that the dielectric being used. So for open wire, it actually uses air as a dielectric. So to keep the distance between these 2 conductors constant, meron lang tayong ginagamit na insulator known as spacers. But it's not put continuously, no? So by segment lang. So para hindi lang mag-touch yung dalawang wires natin. So that would be the construction of the open wire. Whereas pagdating sa twin lead, pinalitan natin yung spacers at saka yung dielectric ng solid talaga, no? So our dielectric dito is air. Our dielectric sa twin lead is solid to keep this distance constant din, no? So at the same time, the dielectric natin is flexible na solid, no? So solid flexible siya. So that would be our twin lead. So kaya nga hindi na natin masyado nakikita yung mga lines na to because they are overpowered na by the dominate na sila ng mga coaxial. So but siguro talking about the Philippines, mga year 80s, 70s, popular pa yung paggamit ng mga twin lead na sa household natin. Yung antenna connected to our TVs are using twin leads pa, no? But ngayon it's more of a coax na. So now let's talk about the coax. The most widely used type of transmission line today is the coaxial cable na, no? So it consists of a solid center conductor surrounded by a dielectric material made of polyethylene, polyvinyl, or Teflon. So that is the insulator na ginagamit. But meron din mga coaxial na air din yung dielectric, but obviously seldom lang din ginagamit yun, no? So this is your solid flexible na coaxial cable. This would be the center conductor right here, and this would be the shield natin na tinatawag, no? So this is braided wire actually, and ito naman yung insulator. So the distance between the outer conductor and the center conductor must be kept constant pa rin by using a dielectric that is solid, and there is a jacket outside as a protector. So that is your coaxial cable. Ito naman yung coaxial cable na rigid air filled. So ibig sabihin, this is a conductor, this is an outer conductor, this is the inner conductor, and what is in between dito sa gitna is air. So para ma-keep yung distance between the outer conductor and the inner conductor, there is a spacer na naman na nilalagay. So itong bilog na to sa ilalim are spacers to keep the distance between the conductor and the inner and the outer conductors constant. So coaxial cable comes with variety of sizes. Meron mga coaxial na ang lalaki talaga, no, with several inches in diameter, but yung nakikita lang natin mostly sa bahay, yun yung mga maliliit na coax like the RG59, no, yung para sa TV, yun yung maliliit. But may mga malalaking coax din na parang waveguide na yung laki, no? So this is an example of an RG59. Ito yung mga pinaka-common na nakikita sa bahay. Solid yung kanyang center conductor, tapos braided yung kanyang outer conductor, and ito yung dielectric material natin na tinatawag. And ito yung protector natin, yung jacket. So that would be the coaxial cable. Now for datacoms, isa sa pinakasikat is yung twisted pair, no? So ito yung tinatawag nating mga transmission lines na ginagamit for datacoms. So this uses two insulated solid copper wires, tapos pinag-twist sila together, no? So ito na yun, no? Ito yung tinatawag nating UTP or unshielded twisted pair, and ito naman yung tinatawag nating STP. So this is STP, no? So STP or shielded twisted pair. So meron siyang shield dito, meron siyang aluminum, sometimes para siyang thin aluminum foil na binabalot dyan, no? So yun na yung magbibigay sa kanya ng shield. So that would be the STP. So this twisted pair originally is used sa telephony, but doon naman talaga nanggaling yung datacoms, no? Sa telephony nag-evolve siya until the voice or until the wires will now carry data maliban sa voice, no? So kaya nga data communications ngayon is naka-base talaga sa backbone ng telephony system. So originally, the twisted pair is used in the telephony, but later on, nakita yung potential niya for data communications. So one of the most widely used wiring in local area networks or LAN is the twisted pair. But obviously ngayon, pumapasok na rin yung fiber optics sa field ng data comms, no? So the Philippines up to this year is investing, the telco industry dito is booming, investing towards the elimination of the copper and replacing the lines with fibers na. So halos lahat ng providers natin are now shifting to the fibers. But we also have a topic na fiber optics, ating telco topic later on sa ating ESAT na subject. So sa ngayon, we'll just need to focus on the original na mga transmission lines, yung mga copper lines na tinatawag. Okay, now kanina, the first requirement to achieve maximum power transfer is to connect balance to balance, unbalance, and imbalance. So we will need to define what is the difference between a balanced line and unbalanced line. So pag sinabi mong balanced line, neither of the wire is connected to the ground. So at least 2 wires yung kailanganin natin para makabuo ng transmission line. And for a transmission line in which walang i-connect sa ground, in short, both of the conductors will carry current, then that will be classified as a balanced line. So both conductors carries current, the same current flows in each wire with respect to the ground, but nobody is grounded. But the direction of the current of one wire is 180 degrees out of phase with the current of the other wire. So it means na dalawang kuryente, one actually goes from source to load, and the other is a return from load back to source. So opposite yung direction nila, and out of phase yung mga waves nila. So because the information or the signal in a balanced line is based sa differential voltage ng dalawang wires, tinatawag isang differential transmission line. So para mas maintindihan natin, ito yung example ng differential transmission line or balanced line. So one current goes towards the load. This one is a current, and another current goes back to the source. And the voltage that could be seen by the load is the differential voltage between these two wires, yung difference nila. So lagyan natin ng values para mas maintindihan natin. So for example, the first current din sa taas is 5 volts yung kanyang magnitude. The first voltage, the voltage at the upper side is 5 volts, and the voltage at the lower side is negative 5 volts kasi equal sila na voltahe, out of phase lang sila. So what really happens here is that yung nakikita ni load at this instant of time halimbawa is 10 volts. So yun yung laman ng kanyang signal. Kumbaga yung information na nakikita niya is 10 volts. Now what if this will be infested with a 1 volt spike? So what if merong noise dyan na equivalent to 1 volt? So the total peak na ngayon dito is 6 volts, di ba? So may positive 1 volt tayo dyan na spike. So the total na value na ngayon dito is 6 volts. But take note that noise will exist not only in this wire, but also on the other wire. So pag may noise dito sa first wire, meron ding exact noise dun sa kabilang wire. So there will be also a spike here na 1 volt. So if this is 1 volt din na spike, then this value here is negative 4 volts. So at that instant of time na may noise tayo, what really is happening is yung 6 volts minus natin sa negative 4 volts para makita natin yung differential voltage is actually the same as walang noise. So it still is 10 volts. So 5 minus 5 minus negative 5 is 10 volts. Diba? Yun yung nakikita niya, 10 volts. But when the noise exists, with plus 1 and plus 1, it goes to 6 volts, it goes to negative 4 volts, and it still is 10 volts. And it will happen along the way, sa lahat ng waves natin dito sa ating transmission line. So kahit may noise pa na mag-exist dito, yung makikita lang talaga ni load is yung signal natin. So that's how this balanced line somehow cancels the effects of noise. So by using balanced line, you could actually reduce the noise into 60 dB or 70 dB. That is not just 3 dB. That is not just 6 dB. No? It is 60 dB to 70 dB, and that is quite napakalaki. No? So that's how good this particular line is. No? Now let's move on to the unbalance. Pag sinabi mong unbalance, parang hindi talaga siya balance kasi yung isa lang yung nag-carry ng current and the other one is connected to the ground, such as the coax. So one wire is at ground potential and the other one is at signal potential. So itong shield natin, ko-connect natin sa ground. Tapos itong center conductor, ko-connect natin sa load. So that would be our connection. So if there will be noise that will be cut, noise magnetic field which will be cut by the other conductor, all the noise na ma-generate dito sa outer shield can never reach the center conductor because nga in between is an insulator. What happens is that this noise will always find its way to the lowest resistance path to the ground, and it will just go here, not reaching the load. So the load now is safe from noise. So yun naman yung noise immunity ni unbalanced line. So kaya nga there is no point of using an unbalanced line if you will not shield or you will not ground the shield. So it needs to be grounded talaga so that the noise na masagap nun is didiretso dun sa ground and will never reach the load. So an unbalanced line can also be referred as a differential T-line or differential transmission, single-ended transmission line rather, no? Single-ended transmission line because nga isa lang yung i-connect mo talaga dun sa load, the other must be grounded. So different from the balance na walang i-ground, both signals or both conductors will carry the current. Okay, so at least na-differentiate na natin yung balance and unbalance. So now, let's move on to the coaxial connectors. Mga specific connectors na ginagamit natin na lumalabas na rin sa board exam. So coaxial connectors are not really just para lang may convenience sa pag-attach and detach ng ating mga coax into the ports and terminals, but also for the integrity. No? So ang hirap din kasi pag yung coaxial mo is sa splice mo using manual splicing lang. Kukonect mo yung mga coax sa mga ports nila by manual splicing, so that would not preserve the integrity and the quality of your transmission. So there may be loose contacts that could obviously compromise talaga sa communication mo. So para fix, fit at saka mabilis ikabit at saka mabilis matanggal, no? So we will need to use specific connectors for specific applications. So these are some of the most popular connectors ng coax, no? PL259, the BNC, SMA, N-type, and F-type connectors. But hindi pa yan lahat, yun yung mga sikat. So titingnan natin ngayon yung PL259 or the UHF connector. So the PL259 connector matches the output connector found on the medium frequency and high frequency receivers. So in short, ito mga application dito mostly nakikita sa mga transceivers. Ano yung transceivers ng HF? Yung mga ginagamit natin sa amateur radio, no? That is the HF or high frequency transceivers, amateur radio, citizens band radio, or in short, yung mga walkie-talkies, kumbaga, no? So doon yung malaking malaking application nito, no? So the PL259 usually joins the RG213 coax. So mamaya i-discuss din natin ano yung impedance ng 213, no? To an HF transceiver. So this is the indication, this is the identity of a PL259, no? Yung coax mo isusolder natin dito sa tuktok or dito sa tip na male ng ating PL259, and it is threaded. So ibig sabihin ikakabit mo to, but ito-turn mo siya until mag-fit yung thread ng male doon sa female nito, no? So that is the PL259. And when you talk about transceivers, ito yung mga kung saan sila kino-connect, no? Sa likod, sa harap, ayan. So that is the PL259. Then we also have the BNC, isa sa pinaka-common na ginagamit o nakikita din natin sa eskwelahan, no? Sa laboratories natin. So pinaka-trademark ng BNC, found on older and larger handheld transceivers, kasi meron din kasing counterpart nito sa ngayon, yung mga modern transceivers hindi na bulky kasi yung BNC, no? Malaki kasi yung BNC. So may mga maliliit na connectors na tinatawag nating SMA. So that is now for the modern naman saka maliliit na mga transceivers. So sa older and larger, BNC is popular. So also used, dahil nga sinabi ko kanina, nakikita ito sa mga paaralan because most of the equipments ng ating paaralan for laboratory such as the modulators, frequency synthesizers are using BNC also para siguro, no? Dahil para hindi madaling masira ng mga estudyante, no? So ito yung characteristic ng BNC is para siyang bayonet, no? Kasi yung B is bayonet. Bayonet type siya. Ibig sabihin plug and twist, then twist and unplug. So this is the lock of the BNC, no? So plug mo tapos twist, fit na yan, no? Fix na yan. Tapos i-twist mo ulit, tapos unplug, ayun, makukuha na. Wala siyang thread na tinatawag, no? But it's bayonet lock na tinatawag natin. So bulky yung BNC. Counterpart nito is yung SMA or subminiature A. So the subminiature version A is a connector found naman in modern and compact, maliliit na handheld transceivers. So BNC is for old and large, SMA is for modern and small, no? So parang ito na lang yung mnemonic mo, small and modern, no? Small and modern. So usually joins handheld transceivers towards the antennas naman, no? Ito yung characteristic ng SMA. Ayan, meron siyang parang bolt na style, no? So para mabilis siyang i-twist, no? Hindi kagaya ng circular na medyo pag halimbawa basa yung kamay mo, so hindi siya nalalak agad masyado. So with this, mas madali siyang i-turn. So that would be the SMA. Then we also have the N-type connectors. Ito yung nakikita sa mga makabagong mga TV. Meron na rin mga N-type connectors sa TV. So this is the most or the lowest loss at the UHF, no? Ito yung kumbaga ginagamit natin for 300 the 300 MHz to 3000 MHz UHF, no? So the connector of choice above 300 MHz or UHF is the N-type connectors because of its lowest loss, no? So ito naman yung N-type connector. So threaded din siya, no? But makikita mo yung difference niyan kumpara sa PL259 because sa PL259 obvious ka, visible talaga yung solder dito, no? Parang may ganyang shape, no? Pag i-solder mo dito, nandito yung solder, ganyan. Then the most common of them all is the F-type connectors. Yung makikita sa TV, no? So the least expensive, pinakamura, kumbaga, no? So widely used for TV sets, VCRs, DVD players, and cable TV. Ito, no? I'm sure everybody have seen this, no? Daling ikabit, hindi nga lang ganun ka-fix, no? Hindi nga lang ganun katibay din yung connection nito, but yun yung pinakamura na available, no? The F-type connectors. Okay, so now let's move on to the transmission line constants. We'll be having two sets of constants. We have the primary and we have the secondary constants. So let's begin with the primary constants. The primary constants are distributed all throughout the transmission line. No? Ito yung electrical equivalent ng ating transmission line. And dito natin makikita yung mga primary line constant. No? So in short, meron tayong inductor, meron tayong resistor, conductance, and we have capacitance. Now this is distributed evenly all throughout the transmission line. Gaano man kahaba yung transmission line. But if the transmission line is medyo mas maliit na siya kumpara sa wavelength natin, mas maganda na i-lump natin yung mga components na to per length na lang. No? So that is why we could simplify it into a form like this, no? Like inductance per length, resistance per length, conductance per length, and capacitance per length. So that would be from distributive na parameters, ginawa nating lump because if we will consider, kumbaga, a specific portion of the transmission line, if the transmission line's length is medyo maikli na masyado kumpara sa wavelength, then much better na i-lump natin yung mga parameters. So ito na yung mga line constants natin. Primary, series inductance, series resistance, shunt capacitance, and shunt conductance that are evenly distributed talaga along the line. Okay, explain natin kung bakit series yung inductance, series yung resistance, tapos shunt yung capacitance and conductance. Now, this series resistor here, actually, this is, ano yung nire-represent nila? So, this series resistor here represents the internal resistance of the wire na ginagamit sa inyong transmission line. So, okay na yan. So, again, yung series resistance is the internal resistance representation. Now, this shunt capacitance is the representation of a conductor here, and an insulator in between, di ba? So, in every transmission line, the wires must be insulated from each other. So, pag meron akong conductor, tapos sa gitna is an insulator, then I have created a simple capacitor. So, yun na yung capacitance na tinatawag natin. So, ito na yung shunt capacitance. Now, alam naman natin na bawat conductor from here to here, halimbawa, is always separated by an insulator, di ba? So, kaya nga, this insulator, aside from nagbibigay siya ng capacitance, nagbibigay na siya ng tinatawag nating conductance. So, conductance, alam natin, conductance is equal to 1/R. So, conductance is the property ng isang material to allow conduction. So, because nga insulator siya, dapat ma-maintain yung pagiging insulator niya, hindi siya mag-allow talaga ng any conduction. Because once yung insulator mo is pangit at nag-allow siya ng conduction along with the transmission of your signal, then at that particular point na nag-conduct yung insulator mo, nag-short yung transmission line mo doon. Ang pangit yun. Hindi na makakarating yung signal doon sa load because nga nag-short siya at some point. So the conductance there should be very small, no? If not zero talaga. No? So if you want to bring this conductance of very small value, then you need to increase the resistance of your insulator to create a good transmission line. So, okay na yan, no? Okay na yan. So, lastly is the inductance ng inyong wire. So, bakit ba may inductance na representation? So, that is because meron tayong dalawang conductors, halimbawa. Now, take note that these transmission lines are used to carry alternating current. So, if alternating current yung dumadalo dyan, then there will be an expansion and pag-collapse ng mga flux na to, no? So, there will be an expansion and pag-collapse ng flux. And meron siyang adjacent na conductor sa kabilang side. So habang nag-expand ito, nag-collapse yung flux natin, parati siyang dumadaan dito sa conductor, making this conductor cut this magnetic flux. Ang sinabi ni Faraday na, as long as a conductor cuts magnetic flux, this conductor will induce its own EMF. So obviously, that will create now self-inductance. So kaya nga merong inductance dito sa conductor 1, ay merong inductance sa conductor 2, kasi nga si conductor 2, meron din siyang kuryente that would expand and collapse, that would be cut by the adjacent conductor sa kabila. So both conductors will experience their inductance. So that's the reason why there is inductance. So if all of these parameters na nadidistribute like resistor, inductor, capacitor, and conductance is i-grupo na natin into lamp representation or lamp model, then these resistors, resistance, capacitance, inductance, and conductance will be now having a unit per length. So they will be normalized per length. So kaya nga kung mapapansin niyo sa mga libro, it would now be inductance per feet, inductance per meter, inductance per kilometer. So yun na yung mga units nila, no? Kasi nga pag naka-lamp na, you will be needing to be very specific of the parameters na primary constants per length na talaga, no? So the lamp model is normally used para sa specific talaga na analysis ng transmission line. And for lamp models, we are assuming that the current in your lines and the voltage in your line will be constant and uniform. So hindi siya nagbabago. And again, sabi ko kanina, this is normally ginagamit natin if the transmission line physical dimension mo is masyadong maliit or maikli kumpara sa actual wavelength mo. So used when the lamp model is used when lambda becomes significantly greater, masyadong malaki yung wavelength mo kumpara sa physical dimensions ng transmission line mo. On the other hand, if the dimensions ng inyong transmission line is kahalintulad lang ng haba ng wavelength, then you may analyze it using the distributive na mga model. Okay, so now let's move on to the secondary line constant. So those are the primary. So for the secondary line constant, we have two specifics. No? We have the characteristic impedance and we have also the propagation constant. So characteristic impedance is having a symbol of ZO. The unit is ohms. And it is the impedance seen looking into an infinitely long line. So pag meron kang line or transmission line na napakahaba, theoretically infinite, whatever is the, halimbawa ito yung transmission line natin, this is the infinite length. So kung ano man yung makikita natin na impedance dito sa input, then that would now be the characteristic impedance. But obviously that is not practical, no? Kasi wala namang transmission line na infinite yung length. So mamaya, sa pag-discuss natin ng mga parameters ng characteristic impedance, we will also talk about the characteristic impedance of a finite line, like yung hindi infinitely long. No? So characteristic impedance can be also referred as the surge impedance. So the other one is the propagation constant, gamma. This is used to express the attenuation and phase shift per unit length of a transmission line, in which we will be discussing this maya-maya. No? Paano ba yung nagbibigay na phase shift ng isang transmission line, ganito sa kahaba, ganito ganyan. This is also referred as the propagation constant. Now to compare the equations for the characteristic impedance and the propagation constant, so we have here the main equation for the characteristic impedance, R plus J omega L divided by G plus J omega C. So you see, these are primary constants. Diba? So then for the propagation constant naman, multiply natin. So ito, R plus J divide G plus JC. Dito naman, R plus J omega L times G plus J omega C. So yan yung kaibahan ni ZO and the propagation constant. Okay, so let's look closely at the characteristic impedance. So characteristic impedance formula is ito, based sa kanina lang. Now at DC, at DC, what is, by the way, omega is equal to 2 pi f. So at DC, this omega becomes 0. This part imaginary becomes 0. Dominated na ngayon with square root of R over G. So ito yung equation natin, the resultant equation, if we will consider the characteristic impedance in DC. But still daw natin ginagamit to because pag sinasabing transmission line, hindi DC yung pinapadaloy mo doon, but radio frequency, which is AC. So in AC, this frequency will reach up to megahertz, kilohertz, gigahertz. So that leaves us with the dominating na imaginary kumpara sa napakaliit na resistance and conductance na to. No? So this will be overpowered sila by the omega L and omega C, leaving us with the L over C kasi magka-cancel din naman to. No? So leaving us with the square root of L over C. So ito naman yun at radio frequency na. No? So at radio frequency, we will be using the square root of L over C, but at DC, we'll be using the square root of R over G. So in wave propagation, this is napaka-significant. No? In our, siguro mga next topic, hindi pa. So mga after next topic natin, we'll be discussing wave propagation and babalik tayo dito. So characteristic impedance is determined only by the physical dimensions of the line. So mamaya i-explain natin yan. And the frequency, the load, and the length, walang effect yan. So changing the length of the transmission line won't change the characteristic impedance. Changing the frequency on the line will not change the characteristic impedance. And even changing, nor detaching, nor shorting the load will never change the characteristic impedance. So the characteristic impedance is only affected by the dimensions lang, no? Ng distance ng wire mo, diameter ng wire mo, yun lang yung nakaka-apekto ng characteristic impedance natin. So let's prove it, no? So let's talk about the characteristic impedance of the commonly used line, no? So for example, the two-wire line. So as you can see, the formula tells us that the two-wire line characteristic impedance is basically the ratio of your distance center to center between these two conductors and the radius of the conductor, no? So yun lang, wala nang iba, no? At the same time, yung relative permittivity, yung dielectric na ginagamit natin, dielectric constant, yun lang. So see, wala ka naman nakikitang frequency dito, wala ka nakikitang length, wala ka nakikitang load. So yun lang talaga yung nakaka-apekto sa characteristic impedance ng isang transmission line, yung dimensions nila, no? So let's try to look at the coaxial. So for coaxial lines naman, it's inside diameter of the outer conductor divided by the diameter of the inner conductor, log times 1/38 over square root of relative permittivity ng dielectric material mo. And again, wala na namang iba pang nakaka-apekto niyan kundi yung dimensions lang din natin. So regardless what transmission line we are dealing with, it really is true that the load, the length, and the frequency has nothing to do with the characteristic impedance. It's always the dimension. So the ratio of your dimensions would really affect sa kabuuan ng inyong characteristic impedance. So that really is proven by these two equations here, commonly used na mga equations natin. Okay, so ito naman yung commonly used lines ng mga characteristic impedance, no? So the pinaka-common is the 50 ohm line. So ito yung pinakamadami, kumbaga, the 50 ohm. Then we have the 75 ohms, we have the 92 ohms. Then sa mga parallel wires, we have the 300 and the 600 ohms, no? So 300 ohms for the twin lead, 600 ohms for the open wire. And all of these 50, 75, and 92 dominated yan by the coaxial cables. So RG8, so 50, RG58, 50, then RG58A/U, 53 na, no? So the same here, RG62U is 92, then RG62A/U naging 93. No? So RG59 sa mga TV is 75. So yun yung mga characteristic impedance ng commonly used line. So kanina, no, sa PL259, used to connect this 213. So 213 pala is a 50 ohm coaxial cable. Now, ano ba yung ibig sabihin ng RG? Ano ba yung ibig sabihin ng A, ng U? So nandito yan lahat. No? So the RG is actually referring to radio guide. So radio guide 8, parang ganun. Radio guide 58, that is the RG. Now pag /U ka, ibig sabihin ng U, general utility, kumbaga general na gamit. No? It can be used generally. Parang kumbaga sa ating terminologies, generic, parang ganun. No? General utility. Now pag meron kang A, B, or C dito, before the U, it means na na-revise na yan. So kumbaga, between the RG58U and the RG58A/U, itong RG58A/U, revision ito ng RG58U. So kaya nga kung isipin, si 58 is 50 lang. But si 58A/U, 53 or 53.5 sometimes. So yun na yung difference ng A and /U lang. So A/U or A/U or /U. So but there could also be and C. Ibig sabihin mas maraming revision na yan. So that's how it how you decode, no, the decoding of your coaxial cables. So again, between or among the coaxial cables, yung pinakamadami talaga is 50 ohms for the reason na majority sa ating mga transmitters are also rated at 50 ohms. So to connect your transmitters to your transmitting antennas, then you need to have a line that is matched talaga doon, which is 50 ohms also. Okay, so now let's move on to the velocity and phase shift within the transmission line. Now, alam natin that the velocity of light is 3 times 10 to the 8 meters per second, but the question is, can this electromagnetic energy travel inside the transmission line at the same speed? So the answer is no. So the answer is no. It will slow down obviously, for the reason na yung dinadaluyan ng ating electromagnetic energy using a transmission line is not vacuum, no? It's solid electric most of the time. So kaya nga mas babagal talaga siya kumpara sa free space, no? So the ratio of the velocity inside the transmission line, known as the velocity of propagation, to the velocity of free space, known as c, is the velocity factor. So ito yung velocity factor na tinutukoy natin, no? The ratio of the speed of the electromagnetic signal in a transmission line, Vp, over the speed of that electromagnetic wave in a vacuum is the Vf, in which we know that this Vf can only be equal to 1 if your medium is free space. If the medium is no longer free space like the transmission line, then we know that this velocity factor can never be equal to 1. It is now lesser than 1. So a lesser than 1 velocity factor means that your Vp is lesser than c, and there is never a velocity factor greater than 1 because there is no Vp that could be greater than c. So kaya nga most of the velocity factor ng transmission line is less than 1. So yung tip nga is kung hindi mo alam, tapos gagamitin mo sa problem solving, assume ito by 0.66. Yun yung pinaka-common na velocity factor for coaxial cables. So pwede mo gamitin yon, pero kailangan mo ring malaman talaga yung mga velocity factors derived from the relative permittivity ng mga materials, and you can read it doon sa libro na ni-recommend natin na basahin ninyo, no? So sabi nga dito, no, the speed of the signal in the transmission line is slower talaga, no, than the speed of the signal in free space, because nga the maximum speed of light or electromagnetic energy can only be attained in free space. And take note, transmission lines, the electric is not free space. Kaya babagal talaga siya doon, no? Now, I want you also to be familiar of these other two formulas, no? Because these are very significant. So, velocity factor can also be solved over using 1 over square root of relative permittivity. So, just to recall, relative permittivity is equal to the permittivity of the material over the permittivity of free space, no? Sana hindi natin nakalimutan yan, no? So, square root of ER, inverse or 1 over the square root of ER na lang, that still is your velocity factor. Then 1 over square root of LC is velocity of propagation. So this is very significant because what if ipapahanap sa iyo yung coaxial cable na characteristic impedance, and we know that the characteristic impedance of the coax is ZO is equal to 138, then log of D over D. Then what if yung binigay is hindi square root, hindi ER yung binigay? So what if yung binigay sa problem is L and C? So if L and C yung binigay, mahahanap pa rin natin yung ER. Why? Because if square root of L and C yung binigay, alam natin na 1 over the square root of that L and C is equal to your VP. And once you have the VP, i-divide natin yung ng C, you get the velocity factor. And once you have the velocity factor, obviously you can find the ER or even the square root of ER kaagad, no? 1 over the velocity factor, yun na yung square root of ER na ilalagay natin dito, no? So we can still solve for the ZO even if the relative permittivity of the material is not really provided. So that is the reason why I want you to really memorize these three, no? Not just isa-isa, no? But as a whole silang tatlo, no? Dapat magkasama silang tatlo kasi nga based sa ating experience sa mga problem ng board exam, these three could be used talaga to solve the other known or the other unknown rather, no? So kaya nga please, no? I-memorize natin silang tatlo talaga, no? So, parang triplet ng mga formulas. Okay, so now let's move on to the length of the transmission line, kung paano sukatin yung transmission line. Now there are two basic lengths ng transmission lines. One is the physical length, yun yung susukatin natin in terms of actual length like feet, meters, miles, kilometers. That is the physical length. But meron na isang length na yung common na ginagamit natin, no? Yung tinatawag na electrical length. So ano ba yung kaibahan ng physical length with the electrical length? Now the physical length actually is the physical lang talaga, no? Like masusukat mo, no? Ilang metros, parang gano'n, no? The electrical length is not having a unit of a length. So hindi siya meter, hindi siya feet, hindi siya mile, hindi siya kilometers, but it is the measurement, the length of your transmission line in terms of wavelength. So yun yung electrical length. So the length of the transmission line in terms of wavelength is the electrical length. So halimbawa, gaano ba kahaba yung transmission line natin? 3 wavelengths long. So yun na yung electrical length na tinatawag. So the electrical length known as greater than 0.1 wavelength can be considered as a transmission line. So kung halimbawa yung line mo o yung transmission line mo halimbawa is less than 0.1 wavelengths long, then hindi natin mako-consider na transmission line talaga yun, no? So masyado yung maikli for a transmission line. So for us to consider a transmission line, at least umabot siya ng 0.1 wavelength. So that's the length to be considered as, kasi nakadepende yung 0.1 wavelength na to, no? It doesn't mean na pag 0.1 wavelength, 0.1 meter yan parate, or 0.1 kilometer yan parate, or 0.1 mile yan parate, no? It depends on the wavelength, and we know that the wavelength also depends on the frequency, no? So kaya nga iba-ibang frequency, kahit isang haba lang ng line mo, like halimbawa 1 meter line, it could somehow be a short transmission line or a long transmission line, depende kung ano yung frequency no? Because 1 meter sa mataas na frequency would be napakahaba, but the same 1 meter sa mababang frequency would be napakaikli. So yun yung point, no? Halimbawa ito 1 meter yung line mo. So this 1 meter is masyadong maikli kung yung wavelength mo ganito kahaba, that could be at low frequency. But this 1 meter, kung napakahaba na rin if yung wavelength mo is ganito lang kaikli, which is at high frequencies, di ba? So kaya nga even this 1 meter only has the same length, 1 meter physically, but in terms of electrical length, it depends kung anong frequency yung dumadaloy dyan. So hopefully na nakita niyo yung kaibahan ng physical length and electrical length. So in transmission line wavelength, we need to make sure na yung wavelength natin tama yung pagkasukat. So we will no longer use this C over F lang. Kasi nga hindi naman umaabot ng C yung speed ng electromagnetic energy sa ating transmission line. So we need to make sure na yung C is not just C, but the actual velocity ng electromagnetic wave inside the transmission line, which is the velocity of propagation. And we know that the velocity of propagation is equivalent to C times velocity factor. So yun na yung ating formula talaga. So sa pagkuha ng wavelength ng ating transmission line, always be sure na you will observe the velocity factor of the line. Because nga without the velocity factor, parang kinuha mo lang yung wavelength ng free space, not the wavelength inside the transmission line. Okay, so because may pagbabagal ng ating electromagnetic energy inside the transmission line, then we could design this transmission line para pabagalin na lang talaga yung ating electromagnetic energy, no? So transmission lines used for this application are referred as delay lines, no? So the velocity of propagation of a transmission line is less than the velocity of propagation in free space. And because of that, we can introduce delay, no? So therefore, any line will slow down or delay any signal applied to it. So if ito yung purpose mo, then your line is made to become a delay line. So for delay line, to solve for the time delay, you can use this formula. Ayan, no? Meron lang tayong i-note dito, no? Na if gagamit tayo ng formula na to, take note that this L and this C is rated as per length. So it could be per foot, it could be per meter, basta per length. Yan, dapat uniform. Oh. So if the inductance is per meter and the capacitance is per meter, what you can find or solve here is a time delay per meter. So in short, if your transmission line is 5 meters, tapos yung nakuha mo is 1 second per meter, then the total delay nun is 1 second per meter times 5 meters. Yun yung total delay. Kasi nga yung masusulatin dito is just the time delay per length. Depende din sa ano yung kinonsider mo ng parameter, no? Is it inductance per meter? Is it capacitance per meter? Inductance per foot? Capacitance per foot? So doon nababase yung unit ng ating time delay, which is second per the length din ng ating inductance and capacitance. So we need to, kumbaga, if the time delay is solved into seconds per foot, then you need to multiply it kung how many feet, no? Para ma-cancel yan, and what you can get is the actual time delay na, no? So i-cancel natin yung distance by multiplying the total distance also of the transmission line. So ito naman ready-made na to para mostly sa mga coax, no? So time delay is equal to 1.016 times the relative permittivity or the electric constant of your coaxial cable. Now, because these transmission lines can introduce delay, alam natin na bawat delay na may experience na isang electromagnetic wave is nagko-correspond din ng phase shift, di ba? So, kaya nga we could also introduce phase shift in your transmission lines, depende din so ano yung amount of delay, no? Or gaano kahaba yung transmission line mo. So, i-connect na natin. So, halimbawa, meron tayong dalawang signals dito. So, one is the original signal. The broken signal is the original signal. And the delayed signal now is the solid one. No? So, masasabi natin na delayed yung solid because yung original sana at this time is 90 na. Pero yung actual natin na signal na na-delay is 0 pa. So dito 0 na, 360 na kumbaga, 270 pa lang yung actual. Dito 270 na yung original signal, yung actual signal natin is nandito pa sa 180. So it's lagged kumbaga, no? Nadi-delay siya. So masasabi natin na yung delay natin is from this point to this point. Yun yung time delay na masasabi natin. And yun na, justify na natin, no? Na every time delay na to actually creates a phase shift also, no? So based on that realization, based on that drawing, alam natin that this phase shift here is 90 degrees, no? Na-delay tayo ng 90 degrees, na-shifted tayo ng 90 degrees. So we know now that this amount of time delay is 1/4 sa total period mo, no? So if we look at the ratio of the time delay to the period, we can say na, oy, this is 1/4, no? Because this is 1/2, this is 3/4, this is total 1. So this amount of delay is equivalent to 1/4 of the period. And this 90 degrees is equivalent to 1/4 of 360. So pwede tayong gumawa ng equation, no? That the phase shift created by this line is equal to the time delay over the period, which is 1/4. So 1/4 times 360, that gives us 90. Or in short talaga, this is just ratio and proportion. So it's just ratio and proportion, no? Time delay over the period equal also yan sa phase shift over 360. Diba? 90 over 360 is 1/4. Time delay mo to period is 1/4 also. So that is now napaka-simple. No? So by using this formula, kahit ano pa yung hahanapin, as long as the two other parameters are provided, wala nang problema. Halimbawa, hahanapin yung phase shift, may time delay and period ka. So alam mo na yung phase shift. Multiply mo lang yung time delay over the period times 360. Or halimbawa, meron kang phase shift, tapos binigay din yung period. So you can now solve for the time delay. So as long as meron tayong tatlong kompleto and isang unknown, we can always use a ratio and proportion for solving that item. Now, another one dito, isa pa sa nakikita natin dito is that kanina, time delay with respect to the phase shift and the total angle natin. But meron din tayong pwedeng i-realize dito na itong part na to na 90 degrees actually is a portion also ng total haba na to, no? Ano ba yung tawag sa total distance traveled by one cycle? That is lambda. So this could be the length of your transmission line, no? So the length of the transmission line can also be solved if you are provided with a phase shift. Like halimbawa, what is the length of the transmission line to create a phase shift of 90 degrees if the wavelength is equal to 10 meters? So we know that 90 degrees is 1/4 of 360. So dapat yung length na to is 1/4 also of 10 meters. So therefore this length is 2.5 meters. Another ratio and proportion na naman na 90 over 360 is actually equal to length over the wavelength. So pwede natin isulat yung another ratio and proportion na to, no? So phase shift over 360 is equal also sa length over the wavelength, in which generally speaking pwede mo idagdag yan dito para isa na lang yung i-memorize mo. Completos recados na yan, no? So in short, kaya-kaya na ma-solve kahit ano dyan, no? Pwede time delay and period, length and wavelength. Pwede phase shift 360, time delay and period. Phase shift 360, length and wavelength. So kayang-kaya nating ma-solve lahat yan. So that is how to get the phase shift, no? If ano yung binigay, time delay, period, length or wavelength, so kayang-kaya na. Or the other way around, no? So what is really important here is wala kang i-memorize, no? Kumbaga naintindihan mo na, this is just basically ratio and proportion, no? Ganun lang sa kadali. Okay, so now let's move on to the resonant and the non-resonant line.